In this lab, we will look at implicit differentiation. We start, as before, by adding our usual libraries. Also, for SymPy, we will add two variables this time, x and y. The goal is to look at this curve, be able to plot it, be able to find derivative of it, and be able to plot a tangent line together with the curve. The first thing we need to do, we need to define our curve. To simplify our life, we should always try to rewrite it in the form expression equals to 0. Therefore, if we have a curve written in this form, we need to move one of the sides to the other side. So as you can see, I will define my curve in such a way, and this is what it will look like. Next, we will look at plotting. There are two main ways of plotting implicit curves. One is to use SymPy command plot implicit. This is a simple way, however, it's not very flexible. Usually it's okay to use it if all you want to do is see shape of the curve. It will not work very well if you need to plot this curve and something else, for example. So we would usually not use this method. The second method is to use Matplotlib command contour and mesh grid. This method is a lot more flexible. However, it requires a bit more code and therefore we would consider it a little bit more difficult method. So first, let's look at first method. So plot implicit, it takes our equation or our expression. Remember, this has to equal to 0. Then we have two more properties. Adaptive is just the way it plots. You can leave it as is. Points is how many points we take, so how precise is our graph. And this is what it will look like. And we can add some limited beautifications from Matplotlib to it. It doesn't work that well, and in fact, if you're using Collab, it will not work at all. So for example, in this case, I'm going to redraw this graph again. I will add more x and y ticks to the uh, axis. I will place a grid. I will also add a title. So as you can see, it kind of works. Notice my title got cut a little bit. So as I mentioned before, it doesn't work that well. Next, we will look at the second method. Now, this is a more complicated method, so let's look at this line by line. The first thing we need to do, we need to lambdify our expression. Our expression has two variables, x and y. So we will lambdify this expression and we'll call it f. In essence, what we are doing here, we are creating a function with two variables. So f of x and y. It accepts two variables, which is our expression, and will give us an answer. Now, of course, we don't want all the answers. What we really want, we want to know when this is 0, right? And this will be our curve. Different values for x and y, of course, may give me different outputs this way. But we only care about the 0 one. Next, we create our figure, and now we create what's called a mesh grid. So what's a mesh grid? In essence, it's a grid of all coordinates. So we let our x vary between -4 and 4. We let our y vary between -4 and 4. And then a mesh grid takes all the possible coordinates where x is between -4 and 4 and y between -4 and 4. This creates our axis, so horizontal and vertical axis. And now we plot our contour, our curve. So we give all the possible coordinates. We find the value at those coordinates. And remember, we only want to know places where our expression equals to 0. So we define that here. We're saying when this is value will be 0. And we'll make it look red. We add our title, grid, and we plot it. And this is what the curve looks like. And you can already see this looks much, much better. Now let's find some specific points on this curve. Let's say I want to know all the points whose x-coordinate is 1.5. So x 1.5 is somewhere over here, and we can see we should have 2 points, one above x-axis, one below x-axis. So all we have to do now is find the y-coordinates of those points. To do that, the first thing we do, we plug in 1.5 for x. So we will substitute x with 1.5, and this will give us an expression in terms of y only. Now remember, the whole expression is equal to 0. So this is in essence an equation with one variable. Now we can solve this equation to find all the possible y that make it equal to 0. So we will solve it, and we get 4 solutions. Now notice that the last 2 solutions, however, are imaginary. You can tell this because they have times I. So we don't care about those, we only need real solutions since we're looking for coordinates. So that's only the first 2. Also note that all the solutions are given in the form of a list. We can see this by these brackets. So we can save our solutions by just picking the first 2 solutions from the list. So we will save y1 as the first element of that list and y2 as the second element of this list. And there we go. Finally, let's look at implicit differentiation. Suppose we want to find the tangent line at the point 1.5 and y2 and plot this tangent line together with the curve. To do that, we need to find dy dx first, so we need to use implicit differentiation. SymPy has a command idiff to do that. So we will write sp.idiff, and then it takes 3 things. It takes our expression, and it takes our 2 variables, y and x. The order in which y and x are written here matters. So if I write y and then x, it will give me dy dx. If I write x and then y, it will give me dx dy, which is not the same. It's also quite useful to add simplify command. It will make your expression look a bit simpler. You can try to see what happens if you erase it, but usually it's a good idea to have it. And so here is our expression. Next, we will plug in our point into our derivative. So we want to plug in 1.5 for x and the y2 for y. We can use subs method again. If we are substituting multiple things, it's easier to use this type of notation. So for x, we're substituting 1.5, and for y, we are substituting y2. This is called a dictionary. So in our case, we will get the following number, and that's the slope of the tangent line. Now to find the actual tangent line, we can use our equation for the line. We will solve it for y here and plug in 1.5 for x1 here, the y2 for the y sub 1 here, and the slope we just found. So that's what we're going to do here. That's our tangent line. So it's y equals 0.286 and so on, x plus 0.4019 and so on. And finally, let's plot this. So most of this code is exactly the same as before. We will add only 2 things here. We will add our tangent line here, so we need to lambdify the tan function. And then we actually have to plot the tangent line. Notice I'm not using here mesh grid. This is not an implicit graph. It's just a normal plot. We will make our tangent line blue. And there we have it. Notice this is this point, and the blue line here is the tangent line at that upper point. Now for the assignment. The assignment for the Lab 3 will consist of 4 problems. The first 2 problems will be somewhat similar to the examples files. It will be about implicit differentiation. You'll be given curves. You'll have to find various things about it. You need to find tangent line. You need to plot the curve and the tangent line and so on. The last 2 problems will be about something called Newton's method. It's one of the methods we can use to approximate zeros of the function. The problem themselves will guide you through all the steps needed. It will explain everything you need to know. You will not need to use implicit differentiation. You will need to know, however, how to find normal derivatives, how to find tangent lines, and how to plot normal graphs.